Okay, welcome back, everyone. This will be the very first lecture in our online adventure. We're going to kind of ease back into things. I know it's been 2+ weeks since we've done any math. At least I haven't done any math. Y'all probably spent hours doing it for fun, but we're going to ease back into it. And so this is the format we're going to be using most of the time. It's going to be a nice black screen, and I have my handy little tablet here, and I can do nice colorful lines with all sorts of pretty colors. And y'all are going to get sick of me doing all the weird colors, but since I have them and I don't have to worry about markers running out or anything, I'm going to use colors because they're fun. So, and then another thing, which y'all know this is one of my biggest pet peeves, I have a board full of stuff, and instead of spending the time erasing it, all I have to do is just do a combination, and boom, it's gone. So, yeah, so here we go. I hope everyone is safe and stays nice and healthy. Let's hope we can ride this out. So, here we go. We're going to start back with a little bit of a review. We're going to talk about, let me go to my favorite. That's going to be my yellow. We're going to talk about functions because that's kind of where we started a little bit ago after the last exam. And when we went over functions, we said that what makes a function is you have some list of inputs, maybe A, B, C, D, and then you've got some list of outputs. And maybe this is 3, 4, 5, 6. And the inputs point to the outputs. And it is a function as long as every input points to exactly one output. So A points to 1, B points to 1, C points to 1, and D points to 1. It doesn't matter that C and D point to the same one. What matters if it's a function is that there are not two arrows coming out of C and not two arrows coming out of any of them. So that makes it a function. We called these, we said this is the inputs and this is the outputs. And then we had an example of ones that weren't function. This is a function. And then as an example of something that isn't a function, let's see, what color would you like for that? Let's go orange. No one likes the color orange. So if I have a set of inputs, Z, Y, X, W, and then some outputs over here, maybe, oh, I don't know, 4, 8, 12, 16. Alrighty, so far so good. Still so far so good. But the second two arrows come off of X, where X is pointing to more than one value, it's pointing to 8 and 12. This is not a function. Doesn't matter what W does at this point. W can just maybe point straight ahead. But this is not a function, which I will abbreviate as func. So that's kind of what we talked about a while back. That's how you represent a function with the inputs and the outputs. And we also gave the inputs a name. We said this is the domain, and the outputs are the range. And we're going to see that several times in the future. So this is the input-output representation of what a function looks like. It is a function as long as every input points to one and only one output. The second you get more than one output, as with X here, it is no longer a function. And so now, with the miracle of quick erasure, I can erase everything. Look at that. That is amazing. So, go back to my yellow. Graphically, it's even easier to figure out what a function is. So I have a graph. Maybe it looks like this. So if you think of your x values as your inputs and your y values as the outputs, maybe this function looks something like y equals x plus 1. Okay? So y equals x plus 1. If I plug in any value in for my x, maybe x is 0. Well, when I do that, what do I get from a y value for my output? Well, y would be 0 plus 1, which is 1. Okay? So I give a single input in, and I get a single output out. This is a function. The way that we can think about representing it is if I give you an x, I only get one y value out. Therefore, if I had a virtual pen, you can imagine this is, I'm going to have to sort of draw this because y'all, I'm not animating this stuff for y'all. Oh, I wish I had my yardstick now. Here's my really well-drawn pencil. Yep, that's it right there. That's my pencil. Y'all can make fun of it. That's okay. So this is the pencil. If I take my pencil and send it vertically across my function, if the pencil touches the graph at more than one point, it's not a function. So as I move across here, maybe you can imagine the pencil is moving right here. It's hitting the function at one point. I keep moving it across. Now it's hitting it again, 1 point, 1 point, 1 point. There's never a point where it touches the graph at more than one location. So this is a function. And the technique here of using your pen or pencil and moving across horizontally, this is called the vertical line test, which I'm sure y'all remember. If it only touches the graph at one point at all times, it's a function. Okay, then we can contrast that with, I probably don't need to get stuck doing orange for the negatives, but I actually like the color orange, but it kind of sings to me that it's not going to be a function. So now if I have a graph that looks like this, oh, maybe it does that. Okay, so in this case, I've got my pencil, which I will draw with a line this time. If I send it across, now as it moves across my graph, if I think about it being at this location, it hits the graph at 2 spots. So for this x value right here, whatever this x value is, I get 2 y values, 2 outputs. So this is not a function. And we typically say that it fails the vertical line test. Vertical line test, VLT. Alrighty? So that's kind of where we started off with the functions. And then we went from there and we did some graphing. So let me kind of shift over and let's do some basic graphing and then we'll kind of continue where we left off. Okay, so let's get into some graphing. So let's look at that. We're going to start off with our standard format. That's y is equal to mx plus b, where m is the slope and b is what we call the y-intercept. And so the reason we call both of these things that is because m tells you how steep or shallow the graph goes up or down. This is a straight line graph. And then b tells you where the straight line hits the y-axis. So if I have something like maybe y is equal to 2x minus 3, well, if I have a graph, 1, 2, 3, 1, 2, 3, 1, 2, 3. Alrighty, so where does this hit the y-axis? Well, it hits at -3, so I'll put a dot down at -3. And then I use the slope to tell me where the next dot is. And the slope is always rise over run, right? So rise over run. And so I can think of, instead of this as 2, I can think of it as 2 over 1. So it is going to go up 2 over 1 for the next point. And then I just connect the dots. And there's my graph. Y'all remember doing that? Alrighty. Hopefully. I can do another quick example, no worries. So let's do another one. Alrighty, maybe y equals -1/3 x plus 2. And draw the graph over here. I'll try not to do the 1, 2, 3 marks. I know that's going to drive y'all crazy on headphones, so I'll try to draw them without actually saying the words. I'm going to forget those, so just wait for it. It's going to happen. Alrighty, so I am looking for where this hits the y-axis for my first point, and it hits the y-axis at +2, so right here, +2. And so I call the 5 number, and this would be 1, 2, 3, -1, -2, -3, +1, 2, 3 on the x, and -1, -2, -3 on the x. So that's how you number your graphs. And so on the y-axis, I put a point at +2, which are right there. And then the next point is going to be the slope of -1/3. So I'm going to have, since this is a negative value, that's instead of the rise going up, the rise is going to be going down since it's a negative value. So this is going to be going down 1/3. So it'll be just sort of like that. That's my next point. I connect the dots, and that's my graph. Alrighty. And before I get off of this, let me remind what this looks like. Y equals 2. So in this example, we are missing that term right there. And the only way that we're missing that term is if x is a 0. So what this basically means is this equation has a 0. Let me rephrase that. I just said that. I just realized I said that wrong. Redo. I'm going to be doing this a lot, so y'all get used to it. The only way that this is 0 is if the value in front of the x is 0. The slope is 0. My goodness, it's been a long day. So if the slope is 0, in other words, if this is y is equal to 0x plus 2, this is the same thing. What this means is that it's going to be the slope is a horizontal line. So a slope equals 0, that is going to be a horizontal line. It's not going up or down, it's literally just a flat line. So what does this look like? Well, at y equals 2, it's a horizontal line, just like that. And this function right here is always, no matter where I am in the x, y is 2. And that's what we have right over here. So if you don't want to think of it having a 0 slope, just think of it as when it says y is equal to 2, it means a line where the y value is always 2. The only type of line that can be is a flat line at y equals 2. So let's do another example of that. Maybe y equals -1. Well, again, that is going to be, I prevented myself from saying the numbers, so I'm getting points for that. So what does this look like? Well, the y value for this equation is always -1. So that is a line that is flat at y equals -1. So that was that side, and then we also said that we could have equations that look like x is equal to 2. Well, using the same analogy, in this line is always x equals 2, and the only type of line that can be is a vertical line that passes through x equals 2. And this, the big question, I'll give you a second to think about it, is this a function or not? This line right here. I know this one is. I can look at it and tell it's definitely a function, because if I move my virtual pencil across the graph, I'm only hitting the actual graph at one location, so it's definitely a function. What about this one? Well, as I move my imaginary vertical line across, everything's fine until I hit right here. And at this location, this x value, x equals 2, has an infinite number of y values. So this is not a function. But you know how to graph it if it pops up. If I give you a real quick, x is equal to -3, what does that look like? Well, 1, 2, 3. It is a vertical line at x equals -3. Not a function, but that's how you graph it. So that's how you graph these things. Now for the fun part. And if y'all can hear that in the background, my cats are running laps around the bedroom for some reason. So you can hear all sorts of fun things in the background, I'm sure. So let's go from basically graphing this stuff into more complicated functions, which is where we left off with piecewise functions. So let's go ahead and tackle that. Okay, let's tackle piecewise functions. Piecewise functions. So piecewise functions, we're going to start off with a real nice simple example, several simple examples, and then kind of build as we go. So the weird thing about piecewise functions is they start out like a normal function, maybe y is equal to 2. I'll draw it over here. Okay, where does that look like? Well, that is going to be a line, horizontal line at y equals 2. Okay, what makes piecewise functions strange is that we don't just give you what the graph looks like, we also tell you where the graph lives, where it's restricted to exist at. So in this case, what if I said it only lives at x values that are greater than or equal to 0? So in that case, remember this is the x-axis, so all of the x values that are equal to 0, right here, x equals 0, and greater than, that's where this function lives. Anything that's not here, that's not defined over here, the function doesn't exist. So I now come down and erase everything that's to the left of 0. Okay, it looks like a little Pac-Man there, but that's okay. So this is the new graph right here. It is not only the graph itself, y equals 2, but it's the restricted domain, the x values that the graph actually lives on. So this one lives at x values that are greater than or equal to 0. Okay, let's do a different example. Let's clear the board. And let's say maybe y equals -1. And it's going to live for x values x less than or equal to 3. Okay, so I'm going to graph it out. Alrighty, and what does this look like? Well, it is a flat line at y equals -1, so There we have the flat line. And now this is my restriction right here. Restriction, I think I spelled that right. This is where it lives. Alrighty. So in this case, it lives for all the x values that are less than or equal to positive 3. So where is x equals positive 3? Well, this is 1, 2, 3. It's right here. So all of the x values that are equal to or less than 3 is where this thing is going to live. So all of these values are fine. Well, I messed that one up. Let me draw a nice, there. Okay, that means that all the values that are greater than 3 don't exist. Okay, so that is what this function looks like now. Y equal to -1 with the domain restriction. The x values that it's allowed to live at are x less than or equal to 3. And since I have this equal underneath here, I put a closed dot. However, if instead of an equal sign, I had a, let's just do a normal less than, no equal sign. Now instead of having a closed dot right here, I would have an open circle. An open circle says this is not equal to 3, but it's all the values that are less than that. So everything right up to the exact value of 3, every value that's less than that, that's where this graph lives. Okay? So now that we have those examples, let's get some slightly more complicated ones. And let's see. Let's go with maybe, if I can clear the screen, let's try y equals x plus 1. And then the domain restriction is going to be x less than or equal to 0. Okay? Well, let's graph this out. I'll try to be a little precise now because it's not just going to be straight horizontal lines. I need like a little macro I can paste a little image, some pre-built axes so I can save the time. Alrighty, so what does this one look like? Well, it hits the y-axis at positive 1, so right there. And then what does the slope look like? Well, the slope, the number that's in front of this x, even though it's not there, is a 1. And a 1 is actually 1 over 1. So this one goes up 1 over 1. And that right there is the next point. So now when I connect the dots, like so, I have my graph. So you graph it like normal, and then after you have your graph, you restrict your domain. So in this case, this function only lives for x values that are less than or equal to 0. So all the values that are equal to 0 and less than 0 are fine. All these values are totally fine. This is where it lives. But all the values that are greater than 0, it doesn't live there. So I get to erase that. And so that right there is exactly what this graph looks like. Okay? All right, let's do some more examples. Okay, so let's say that we have y is equal to 2x minus 2, and the domain restriction is going to be x greater than -1. Okay, so we're going to graph it just like we did the last one. Let's see. Okay, so where does it hit the y-axis? Well, it hits it at -2, so y equals -2 is where we put our first dot. And then we have a slope of the 2, which is 2 over 1. So it's going to go up 2 over 1 for the next dot, and then we connect those dots with our line. just like that. And now we look to see where it actually lives. And this function lives for all x values that are greater than x equals -1. So we come over to x equals -1, and right here is where x equals -1, and it lives for all values that are greater than that. So all of these values right here, all of these are good. Okay, so it doesn't live at any values that are less than or equal to -1. So I just bring out my trusty eraser, erase that. And last thing is, since there's no equal sign here, instead of a closed circle, I do an open circle right there. And that is how this one is graphed. And another little trick that someone in class mentioned this, I don't remember who it was, but it was a great little trick, is if you want to know where these things are defined, the direction of the inequality here tells you. So where does this function define? Well, it is, see how the little arrow is pointing this way? It's all the values that are this way from x equals -1. So x equals -1, and then all the values that are that way. That's what that little greater symbol says, is to move in that direction. So that's kind of nice. Alrighty, so let's do another example. Let's get a little bit more interesting. Let's try y is equal to 2/3 x minus 1, and the domain is going to be all x greater than or equal to 2. Okay, and draw it out like this. Okay, now where does it hit the y-axis? Well, at -1. So put my first dot there. And then what does the slope do? Well, this one is going to go, it's got a rise of 2. So that's my rise. It's +2, so it's going to head up. And my 3 is my run. And run is always defined in that direction. So if it is a positive slope, the rise is going up. If it's a negative slope, the rise is going down. But the run is always in this direction. Okay? So here we go. I'm going to go rise of 2, so 1, 2, and then over 3. 1, 2, 3. Just like that. Then I connect the dots. Okay, there's my function. And now I have to restrict the domain. And so this is all x values that are greater than or equal to +2. So I come over to x equals +2. That is 1, 2, so it's right here. And so all of the values that are greater than or equal to -2, and this little arrow here, which is kind of incomplete, I drew it fast, is pointing in that direction. So all of these values are where the function actually lives. This is the legit area. All of the other ones, it does not live there, so I erase all of those. And it's a little heavy-handed. I think I need a shorter, smaller eraser. But this is what the function looks like. Just this right here. It is this function restricted to a domain of all the x values that are greater than or equal to 2. And this is x equals 2 right here. Okay? One last example. This is for all the marbles. Here we go. Y equals -1/2 x plus 2. And then we're going to restrict the domain x. Oh, let's try greater than -2. Okay, so here we go. I'm going to draw it out. Let's see. Okay, so where does it hit the y-axis? Well, over here, this hits the y-axis right there. It's the y-intercept. So at +2. Okay, and then what's the slope look like? Well, It's a negative 1 over 2, so it's going to be down 1 over 2. That's going to be my next point. I'm going to connect the dots. Try to actually connect the dots rather than being way outside of them. So there, you saw nothing. Alrighty, so it was assuming that I could actually draw that and pass through y equals 2. So this is what the graph looks like. This tells me where it lives. Where does it live? Well, I look at x equals negative 2. This is right here, x equals negative 2. And it's all the values that are greater than that. So it's going to be all of the values. This is x equals negative 2, all the values that are greater than that. So all of these values right here. Okay? Now, since there is no equal sign under here, it not only doesn't include the values that are less than 2, but it doesn't include negative 2. It also doesn't include negative 2 itself. So I have to indicate that with an open circle at x equals negative 2. And you can see from that little arrow, this is the direction that it lives in. X equals negative 2, right here, everything that is to the right of that. So all the values that are greater than that. This is where the function is defined. Okay? Whew, we're almost there. Here we go, last piece. Okay, so now we're actually getting into the real piecewise part. And up till now, we've just been doing functions with domain restrictions. But now we're going to do piecewise. And what makes it piecewise is the format. So the format is, instead of saying y equals, we say f of x equals, and remember f of x is very similar to just saying y. So f of x and y are pretty much synonymous because y, the y value you get out of all the previous functions, well, you get that by plugging in an x value into the function. So that's why f of x and y are pretty much the same thing. So we start off with an f of x equals, and then we do a curly brace, if I can actually do this. Whew, for a second I couldn't draw it. And then we have two functions that are defined, or more, but we'll start with two. Maybe 2, comma, x less than or equal to 0, and negative 1, x greater than 0. Okay, it looks really complicated, but it's not. The main takeaways from here is that we first have to decipher what this is. This does not look like what we're used to, but this f of x equals, and then these values, that's the same thing as y equals these values. So what I do every time I graph these things, I put a little y equals in front of whatever's over here on the left. This is the function definition. This is what tells you what the function is. And this f of x is the same as y. So instead of just having it kind of isolated here, 2 and negative 1, I put the little y equals 2, y equals negative 1. I do it explicitly. Y equals in front of each of my little definitions here. And each of the functions has a domain restriction over here. And that domain restriction is a little more important to be careful when you have two functions that you're graphing, because the domains can't overlap. The top function lives for all x values that are less than or equal to 0. The bottom function is going to live at x values that are greater than 0. There's no overlap between these two sets of x values. So let's graph this out and see what it looks like. We start off. The way you do these piecewise functions is you treat them exactly the same. Absolutely no different than what we've been doing. And so we start off, we have the very first function, y equals 2. What does that look like? Well, y equals 2 is a horizontal line where all the values are y equals 2. So it is a straight line right there at y equals 2. Okay? Now that I have graphed that, I restrict the domain. What values does this live under? Well, it's all the x values that are less than or equal to 0. So all the x values that are equal to x equals 0, which is right there, and less than that. So all of these values. Okay? It doesn't live anywhere else. So I simply erase all of that. Okay? So that's the first function graph. Now I move to the second function graph. Y equals -1. What does that look like? Well, it is a horizontal line, which that's the worst horizontal line I think I've ever drawn in my life. But that's okay. It is a horizontal line at y equals -1. So there it's supposed to be horizontal. Where does it live? Well, it lives for all values that are greater than 0, but not equal to 0. So it is not including 0, but it is all the values that are greater than 0. So what do? Well, I want to erase all the values that are less than. So I grab my eraser and I erase this. Took a little chunk out that way. And now since it doesn't include 0, instead of a closed circle, I do an open circle. Okay? So now I have, this is the completed graph of the piecewise function defined above. The first function, y equals 2, it lives for all values of x that are less than or equal to 0, so everything equal to 0 and to the left. The next function, y equals -1, it lives for all values of x that are greater than 0, so it is all the values that are greater than 0 but not equal to, so we put the open circle right there. And that's it. That is how you graph a piecewise function. Okay? Now, life would be pretty boring if all we had were y equals 2, y equals -1, y equals 5, etc. We don't want just horizontal lines, we want actual functions. So let's draw an actual function and see what it looks like. So clear in the board. Let's try f of x equals, here we go. Let's try x plus 1 when x less than or equal to 0, and maybe 2x minus 2x greater than 0. Okay? First thing I do before I do anything else is I put that little y equals in front of each one of them. Y equals, y equals. That way it looks like the y equals mx plus b format. Okay? So I'm going to go down to my graph right here, draw some marks. Okay. I don't know if y'all would prefer silence or the tick marks, because the silence is getting a little silly. So, anyways, that's okay. So we start off with the very first function. We need to graph it in its entirety across the whole thing. So what does this look like? Well, it hits the y-axis at +1. Okay, so right there. And it goes up 1 and over 1. That's what the slope of 1 is. So up 1 over 1. So that is the next point. Then I'll connect the dots like so. Okay. And now that I have fully graphed the function, now I can restrict the domain. Where does this live? Well, it lives at all x values that are less than or equal to 0. So it includes 0 and everything to the left of 0. So all of these values are good. All of these values are not, so all I have to do is erase them, like so. Okay, now that is the first function, graphed and restricted. Move to the next one, y equals 2x minus 2. Where does this hit the y-axis? Well, at -2, so right down here is my first one. What does the slope look like? Well, it's +2, so this is a 2 over 1, right? So this is going to go up 2 over 1. So there's the next point. And then I'll play connect the dots with this. Okay. Now, where does it live? It lives, its domain is all values of x that are greater than 0, but not equal to it. So it's in that direction from x equals 0. So there's x equals 0. So all of these values to the right are included. Everything to the left is not, so I can erase it. And since, yeah, I need a small eraser. Since I am not including x equals 0, I put an open circle right there. And now I have my fully graphed piecewise function. This is the first function, restricted to values that are less than or equal to 0. This is the second function, graphed for all, and restricted for all values of x that are greater than 0. And that's it. That's the way you graph these. I'm going to give 2 more examples, and then I think we will wrap this up. Okay, let's say that we have f of x equals, let's do 2/3 x minus 1, and we'll restrict that for x less than or equal to 2, and negative 1/2 x plus 2, and then x greater than 2. Okay, so let's draw it out. 1, 2, 3, 4, 1, 2, 3, 4, 3, 4, 3, 4. I think I like that better in silence. So if y'all really hate it, send me a quick email. So first thing I do before I start to graph it is I do my little y equals. So y equals, y equals. Okay? And now I just focus on the first one. Y equals 2/3 x minus 1. So where does it hit the y-axis? At minus 1. And then what does its slope look like? Well, 2/3. So up 2 over 3. 1, 2, 1, 2, 3. So that's going to be the next point right there. And I'm going to connect the dots like so. And let's see, where does it live? Where is it restricted? Well, it's restricted to live at all x values that are less than or equal to 2. So at x equals 2, it includes that value and everything that is to the left. So all of these values is where it lives. And so I now erase, and make my eraser a little bit smaller, everything to the left, to the right of that. Okay? So that is the first one, restricted, graphed and restricted. Now let's move to the next one. And so for the next one, I have y equals negative 1/2 x plus 2. So where does it hit the y-axis? Well, at plus 2. And what does its slope look like? Well, negative 1/2, so it's down 1 over 2. So something like that. And down 1 over 2. Now I play connect the dots. Oh boy, that's not a good connect the dots. That's okay though. Okay, there's my graph of y equals negative 1/2 x plus 2. Now where does it live? Well, it lives for all values that are greater than 2 but not equal to 2. Well, right here is at x equals 2. And so it's going to live on all these values, but it is not going to actually equal the value 2. So when I erase everything over here, like so, I need to make sure that the circle that indicates x equals 2 is open because it does not equal that value. So this one is y equals negative 1/2 x plus 2. That's that function. And this function is y equals 2/3 x minus 1. And that's it. That's how you graph this piecewise function. You graph the whole function, and then you restrict the domain. You erase everything that isn't included in this little domain restriction. And then you move to the next equation, the next function, graph it, and restrict its domain. And one thing to notice is that if I take my pen and move across, you can imagine a vertical line moving across the graph. Over here, it only hits the graph at one location, and then at x equals 2, it still only hits the graph at one location because this function includes the value, this function does not. So at x equals 2, it's still a function, and so then it keeps moving, and still it only hits it at one location. So this is a function. Even though it's defined in two pieces, it's still a function. Okay? Now, for all the marbles, here we go. This is going to be the big one. All right. You ready? F of x equals, here we go, x plus 2 for x less than or equal to negative 1, 3 where x is between negative 1 and positive 1, and that's not supposed to be like that. Can't have include the same values. And then let's do negative 1/3 x plus 1 where x is greater than 1. Alrighty, so these domain restrictions, I have x less than or equal to negative 1, x between negative 1 and positive 1, and x greater than positive 1. Okay, so we have three functions to graph, and they're not as bad as you might think. So, you know what I'm going to do? I'm going to do something cool. Y'all bear with me. This one, let's graph the first one like normal. Let me graph through the little lines. Oh, I think you're going to like this. 1, 2, 3, 1, 2, 3. Okay, and that is a third. That's supposed to be a 3 right there. Okay, so we graph the first one, x plus 2. Well, before I do that, what does that mean? Well, nothing until I remember there's a little y equals in front of each of these, right? Y equals, y equals. So here we go. Y equals x plus 2. So I've got the y-intercept at positive 2. And then what is the slope? It's a positive 1, so it's going to go up 1 over 1. Okay, so it is going to look like something like that. Okay, now where does it live? Well, all values that are less than or equal to x equals negative 1. So this is x equals negative 1 right here. So all the values that are equal to that and less than that. So all these values, where it lives, which means it doesn't live anywhere else. So I now can erase everything else. So erase all of this. Okay. And make sure that I put a nice big circle there to indicate that at x equals negative 1, this function includes that value. Okay. Now for the next one, which if I had been thinking I would have done all along, I'm going to do this one in green. So here we go. Y equals 3. What does that look like? Well, y equals 3 is a horizontal line at, wouldn't you know it, y equals 3. Okay? Now, where is it restricted? Well, this one lives between negative 1 and positive 1. So, negative 1, x equals negative 1, and x equals positive 1. It's going to live in between these two values. So it doesn't live anywhere else. I can erase all the rest. So I'm going to erase all this. And erase all this. Okay. Now, the only thing I need to do is be careful with the endpoints, because x does not include the -1, but it does the +1. So when I'm doing this, I've got let me erase this to put a open circle for x equals -1, because there's not an equal sign underneath here, but a closed circle at +1, because it does include that value. So this one is y equals -3. That's the function that went across like that. And it's restricted to live between -1 and +1. X equals -1, x equals +1. That's where it lives. And it doesn't include the -1, so open circle, but it does include, since it's equal, the +1, so it's closed circle. Alrighty? Now let's do the next one in blue. So we've got y equals -1/3 x plus 1. Where does this hit the y-axis? Well, at +1, so y equals +1 right here. And then what does the slope look like? Well, -1/3, so down 1 over 3. So that's going to be the next point. And draw this out, connect the dots, like so. Okay, now that I have graphed the function, I can now restrict the domain. It is all the values of x that are greater than 1, but not including 1. So this is right here, x equals 1, right? So these values, but not including it, so I need to erase it. It includes all of these values that are this direction from 1, right? So all these ones to the right are included, and nothing to the left, so I get to erase all of this. Okay, and since I am not including 1, I have an open circle right there. Okay, so here we go. This is it. This is our function, our piecewise function graphed out. First function, we have y is equal to x plus 2. So that's this one right here. Okay, the next one, y equals 3. And so y equals 3. And then the last one, y equals -1/3 x plus 1. And notice, again, if I take a vertical line and move it across, at y equals 1, there are not two values there. The first function includes that value, the second one doesn't. And I keep moving across. At y equals +1, the second function includes that point, the third function does not. So it is there. This is a function. So this one is a function. It is just a piecewise defined function. It's defined in 3 pieces. And as I mentioned in class, why on earth would you ever want this? Well, you can imagine you're doing you have an equation that's describing a chemical reaction where maybe this axis is time, and at a certain time, maybe it's a steeply rising reaction, suddenly it flatlines, nothing happens, and then whatever you're trying to do starts to decrease at another point in time. So the piecewise functions are what really define lots of real situations, because there are lots of times you have jumps in whatever you're doing. You turn a switch on, you suddenly a chemical reaction begins, you name it. Sudden jumps occur all the time in the real world. So these things are actually really useful, and I wish I could say you won't run into them too much as you go, but that is not the truth. Since they are what governs, what actually describes reality, you're going to see them a lot. in any science that you do. So you're stuck with them from now on. So good thing to make friends with them. Okay, so I'll give y'all a few, probably three homework problems, and we will wrap this up. So let me give you these three problems. Okay, so here's the homework. Uh, Three problems, graphing out piecewise functions. This will be the homework that we go over next class, which should be somewhere around Wednesday when I have the next video out. So good luck graphing them. If you have trouble at the beginning, no big deal. These things just take a little bit of practice. And we'll go over them thoroughly at the very beginning of the next class. And that'll be about it. So good luck. Um, I think this is going to be a really good semester. I think y'all are going to enjoy being able to rewind and see exactly what I did when I did it and everything at your own pace. So hopefully this will go well. So I will see you next class. Send me an email or anything if you need any help between then. I should get my office hours up for a Zoom within the next day or so. All right. Take care. Bye bye.